Welcome back to the Deep Dive. Our mission here is simple. We take the most complex technical documentation, the kind that makes you cross-eyed, and turn it into a fast, engaging shortcut to being truly well-informed. You don't just get the summary, you get the unexpected insights.
And today's deep dive is absolutely essential for anyone working with modern infrastructure. We are moving beyond the simple concept of just plugging in a cable.
Right.
We're going to understand the intricate negotiations that happen, instantaneously when you connect a device to a switch port. Our focus is the foundational mechanics of network links, specifically Layer 1 and Layer 2 covering speed, duplex, auto-negotiation, and, crucially, how to spot the hidden dangers, like configuration mismatches.
The complexity starts with the medium itself, doesn't it? I mean, if we were only dealing with fiber optic cables, the challenge would be, well, minimal.
Pretty much, yeah. Fiber is generally plug and play. The light transmission either works or it doesn't. But we are focusing on UTP unshielded twisted pair, that common copper Ethernet cable you use every day.
And UTP requires sophisticated handling because of the various speeds. You've got 10 MAPs, 100 Mbps, 1,000 Mbps.
And the different cable types, straight through versus crossover, plus that tricky concept of duplex settings.
Right.
The problem is that UTP links need to solve a fundamental chicken and egg scenario. Two devices need to agree on how fast and how efficiently to communicate before they've even decided on the physical signaling standard they will use.
So our mission today is to dissect these automatic processes that are supposed to make it work.
And uncover the surprisingly severe operational pitfalls that happen when those automatic processes break down or, get manually overridden.
Okay, let's unpack this multi-speed reality first. Looking at any modern network interface card, whether in a server or a laptop, you'll likely see it labeled as supporting like 100, 100, 1,000 Mbps. This adaptability is the key to scalable networks, right? You don't want to be locked into a single speed.
Exactly. It's adaptability by design. Imagine replacing every device on your network just because you upgraded your core switch to gigabit Ethernet. It would be, a monumental waste of resources.
Yeah, totally.
Modern hardware has to support multiple standards, 10 base T, 100 base TX, 1000 base T, so it can interoperate with devices built across decades. But like you said, this creates the negotiation problem.
So how does the switch, which might support 3 speeds, talk to, say, a legacy printer that only supports 100 Mbps? They need some kind of universal language, a handshake mechanism.
And that mechanism is the IEEE standard for auto-negotiation. When it's properly implemented on both devices, it really represents the ideal state of link configuration.
Oh.
This process ensures that both ends of the link agree on the fastest possible common standard and most efficient communication mode.
And what is that universal language, the one that works even before the physical standards like 100 base TX are actually established?
This is one of the most clever details in networking, I think. They communicate using something called fast lane pulses, or FLPs.
FLP.
This is the crucial mechanism detail. When a device is first powered up, or a cable is plugged in, it sends out these bursts of electrical energy, the FLPs, which carry specific data encoding its full capabilities, like I can do this speed, this duplex.
I always find this surprising. We think of data transmission as, steady streams of ones and zeros, but this is like a pre-communication communication. How are these pulses even distinguishable from the standard data signaling?
Because they use out-of-band electrical signaling. Think of it like this. Your laptop needs to agree with the router whether they'll speak English, Spanish, or French. They can't just start shouting.
Right.
The FLPs are a dedicated, low-level Morse code, you could say, that is electrically separate from the eventual data transmission signal. They literally declare, I support 10 millips half full, 100 millips half full, and 1,000 millips full.
So the devices listen to the neighbor's FLPs, figure out the intersecting capabilities, and then they apply a strict set of rules. What are those rules of agreement that dictate the final link parameters?
Well, there are 2 simple hierarchical rules. Rule number 1, choose the fastest common speed. That's priority 1. You want the highest throughput possible.
Makes sense.
Rule number 2, choose the best duplex supported at that speed. And full duplex is always preferred over half duplex.
Because full duplex lets you send and receive at the same time, basically doubling the efficiency.
Exactly. Simultaneous sending and receiving.
Okay, let's run through the illustrative scenarios provided in our source material. This should make the negotiation logic clearer. We have a modern switch. All ports support 100, 100, 1,000 Mbps, and we assume every device is correctly running auto-negotiation.
Right, the ideal setup. So scenario 1, PC1 connects to the switch. PC1 is an older machine, only capable of 10 MBPs, but it supports both half and full duplex.
Okay, so the switch supports 10, 100, and 1,000. PC1 only supports 10. The fastest common speed is clearly 10 Mbps.
Correct. And since both devices support full duplex at 10 Mbps, that's a 10 base T standard, they choose the best duplex according to Rule 2.
So the result is 10 Mbps, full duplex, optimal for PC1's limits.
Perfect. Scenario 2. PC2, maybe a middle-range device, supports 10 and 100 mPs, again, with full and half duplex options.
Ah, so this changes the common set. The switch has 10, 100, PC2 has 10, 100. The fastest speed they both support is now 100 millips.
Exactly. The fastest common speed jumps to 100 mPs. They apply the duplex rule again.
And land on 100 millips, full duplex.
Right again. And finally, scenario 3. PC3, maybe a modern server, supports the full range, 100, 1,000 millibps.
So now it's a perfect match. Switch does 100, 100, 1,000. PC3 does 100, 1,000. Fastest common is 1,000 millips.
Yep, 1,000 mbps. Now, it's critical to note here that 1,000 base T, which is gigabit Ethernet over copper, physically requires 4 pairs of wires for simultaneous transmission and reception.
Oh, right.
But because of that, it must operate in full duplex. There's really no half duplex option for gig copper.
So the negotiation settles easily on the highest standard, 1,000 millips, full duplex.
That's it. That system is elegant, efficient, and provided both sides are speaking the FLP language, it always finds the optimal connection.
But what happens when that trust is broken, when one side isn't playing by the auto-negotiation rules?
And this is where we move from that ideal state to, well, the common operational headache. Cisco and really all networking standards bodies strongly recommend using auto-negotiation on both ends of an Ethernet link.
Always the best practice.
Absolutely. If you absolutely must disable it, maybe you're connecting to some specialized piece of hardware that doesn't support it well, you have to manually configure both the speed and the duplex settings. And, critically, ensure they're identical on both sides.
So what happens when we violate that rule? Let's say we connect a device, maybe an older firewall or just a switch port, forced into a static configuration where auto-negotiation is turned off. This static device sends data frames, but it refuses to send those crucial fast link pulses.
That's when the auto-negotiating device, usually our switch, has to fall back to something called parallel detection logic.
Parallel detection, okay.
It recognizes it's not receiving any FLP, so it realizes, okay, my neighbor is statically configured. It must then try to guess what that configuration is.
How does a switch guess the speed if it hasn't negotiated the standard using FLPs?
It becomes a bit of a digital detective. It actually analyzes the incoming physical electrical signal itself. The signaling scheme for 10 base T uses a different voltage pattern and pulse rate than 100 base TX.
Ah, so it's looking at the raw electricity.
Exactly. By analyzing the frequency and amplitude of the incoming electrical wave, the auto-negotiating device can usually successfully detect and match the physical layer standard being used by its neighbor, so it can configure the speed correctly.
Okay, speed is solved, but this leads us straight into the danger zone, right? The duplex default.
Precisely. Once parallel detection has successfully determined the speed, it has to guess the duplex setting. And here's the rule that just cripples networks all the time. If the detected speed is 10 millips or 100 millips, the auto-negotiating device defaults to half duplex.
Half duplex? Why on earth half duplex? Why not assume full?
It's basically a conservative assumption made by the engineers who designed this years ago. The thinking was, if you're dealing with a legacy device that isn't auto-negotiating, it's safer to assume it might be connected to older shared media infrastructure, like a hub.
Right, where half duplex is mandatory.
Or it simply might not reliably support full duplex, even if it's running at 100 begs. By defaulting to half duplex at these lower speeds, the device ensures compliance with CSMPD.
CSMATI, carrier sense multiple access with collision detection. That's the system required for half duplex links, isn't it?
Correct. CSMATI is the operational protocol for half duplex. It means a device has to listen before talking. That's the carrier sense part. If it senses traffic, it waits.
Okay.
If two devices happen to transmit simultaneously, they detect collision, send out a jam signal to make sure everyone knows, and then wait a random amount of time before trying again. This whole system is absolutely mandatory for shared media like hubs and required for any half duplex point-to-point link.
Okay, now let's run the common, absolutely devastating scenario. We have PC1, maybe someone manually set it to 100 millips full duplex, maybe they thought they were optimizing it.
Right, a common mistake.
The switch port connected to it is using auto-negotiation. It receives frames from PC1, no FLPs, so it falls back to parallel detection. It correctly senses the 100 millip's speed from the signal.
But following that dangerous default rule for 1031 at speeds, it configures itself to half duplex.
The link status lights turn green. Up, up. Everything looks fine if you just glance at the switch or check basic status.
It's perfectly healthy, but you have a severe duplex mismatch.
Walk us through the disaster this causes. Why is the performance so incredibly terrible?
Because the two ends are playing by completely different rule books. The full duplex PC believes it has dedicated transmit and receive pairs. It does not run CSMAND. It just assumes its transmission channel is always clear, so it transmits frames whenever it feels like it.
Like it has a dedicated lane on the highway.
Exactly.
Okay.
Meanwhile, the half-duplex switch port is religiously obeying CSMAND. It's listening carefully.
So what happens first?
Well, let's say the switch has data to send. It listens. If the PC is already transmitting, which it often is because it's full duplex and never stops to listen, the switch senses that traffic and assumes the medium is busy. So it just holds its transmission. That creates massive latency and delays right off the bat.
Okay, bad start. But the real operational catastrophe happens when the switch finally decides the coast is clear and tries to send, right?
Yes. Let's say the switch starts transmitting a frame. Because the PC is full duplex, it completely ignores the switch's transmission. It doesn't listen. It might send its own frame at the exact same time. The half duplex switch detects this simultaneous transmission. It hears the PC's signal basically trampling over its own signal, and it screams collision, according to its CSMAND rules.
So the switch immediately stops sending, blasts out that jam signal, backs off for a random time.
And then tries to resend the same frame later. This leads to constant retransmissions, exponentially increasing latency, and often significant packet loss. If you look at the actual throughput, it might be running at like 1% or less of the potential 100 billipiece speed.
Wow.
It's a classic example of a silent killer in networking, completely hidden by a seemingly healthy up-up link status.
That distinction between 10, 100, and 1,000 is also worth really emphasizing here. We noted parallel detection defaults to half duplex at 10, 100 millip's. What about gigabit?
Yeah, that's different. 1,000 base D gigabit over copper is electrically engineered in a completely different way. It physically requires all 4 pairs of the UTP wire and uses complex cancellation techniques to achieve simultaneous transmission over all pairs.
Okay.
Because of its inherent electrical complexity and dependence on all pairs working together, 1,000 base T simply cannot run in half duplex efficiently. It's just not designed for it.
So the fallback logic is smarter there.
It is. If parallel detection detects a 1,000 Mbps signal, it correctly assumes and applies full duplex. The danger of the duplex mismatch is largely contained within that 10 Mbps and 100 Mbps range, where half duplex was historically more common.
It's also interesting, just briefly, to connect this back to really ancient infrastructure. LAN hubs, those old non-switching shared media devices, they don't participate in auto-negotiation at all, right? They don't forward FLPs.
That's a great connection. Any device plugged into a hub immediately triggers the parallel detection rules on the device's NIC. The device senses the incoming traffic but gets no negotiation pulses back. So it defaults typically at 10 Mbps, often the hub's base speed anyway, and crucially, half duplex, which is exactly what a shared media hub requires for collision management using CSMAND. It's the only way those legacy shared systems could even function.
So auto-negotiation is clearly the gold standard, the recommended way. But the reality of a network sometimes forces manual intervention. We need to be able to dictate the speed and duplex settings precisely. Let's dive into the command line interface, CLI commands we use to take that administrative control.
Okay, yeah. The commands are pretty fundamental to switch configuration. Once you're in the interface configuration mode for a specific port, you use speed followed by 10, 100, 1,000, or auto.
And duplex followed by full, half, or auto.
Exactly. When you manually set both of these to something other than auto, the switch essentially stops sending those FLPs. It just assumes its neighbor is going to match its configuration exactly.
And if the two manually configured ends don't match standards, if I set one to 100 full and the other to 1,000 full,
the link simply fails to connect. It won't come up at all. Down.
Okay. Now, once we've typed those commands, how do we, as the network engineer, verify what the switch is actually doing? Did it apply my manual setting, or did it somehow end up auto-negotiating anyway? This verification is crucial.
This is where that small yet incredibly critical detail in the output of the show interfaces. Status command saves your day. The little A prefix.
The tiny a is the tell. the giveaway.
It is absolutely the Rosetta Stone of interface configuration verification. If you look at the speed or duplex column in that output and see codes like a full or an A1000, the A stands for auto-negotiated.
Meaning the switch learned that setting dynamically via those FLP exchanges.
Correct. If, however, you see just full, or half, or 10, 100, 1000, without that A prefix, it confirms that the setting was manually configured by an engineer using the speed or duplex commands.
That is the fastest way to confirm whether your administrative intent actually translated into reality on the port. Indispensable for spotting misconfigurations or unintended auto-negotiation.
Absolutely.
Now let's talk about a CLI hidden gem or maybe a point of confusion that often trips up newcomers. Defaults. If I explicitly type the default commands, speed auto and duplex auto, where do they actually show up in the configuration?
Well, often they don't show up in the show running config output. That command is designed primarily to display only the configurations that deviate from the factory default settings.
To keep the config clean, showing only the changes.
Exactly. Since speed auto and duplex auto are the default settings on most modern switch ports, typing those commands and then viewing the running configuration will usually show nothing under that interface regarding speed and duplex.
So the absence of the speed or duplex commands in show running config actually confirms that the interface is currently using its auto-negotiation defaults.
Precisely. If you do see speed 100 listed under an interface in the running config, you know immediately someone manually intervened.
Okay, that makes sense. And since networks are complex organisms, documentation is crucial. We can actually document our intentions right on the interface using the description command, right?
Absolutely essential. The description command allows, I think, up to about 200 characters of text to label the purpose of that link. It's vital human context.
Like, uplink to core switch 3, port 4, using 10G link, or connects to printer and accounting depth.
Exactly. When you're troubleshooting a crisis at 2 a.m., scrambling through connections, that description can be an absolute lifesaver. It tells you what should be there.
There is a slight caveat when viewing the description, though, isn't there? Depending on the command.
Yes, good point. If you run the quick summary command, show interface's status, the description field is often truncated just to fit everything on one line efficiently.
So you might only see the first 20 or 30 characters.
Right. To see the entire full description, maybe up to that 200-character limit, you need to run the more detailed command for that specific interface, like show interfaces gigabyte Ethernet 101. Use the right command for the right level of detail you need at the time.
Speaking of efficiency, if I have to roll out the same configuration, say setting a standard description or maybe disabling a feature across a whole bunch of ports, maybe ports 5 through 15, repeatedly typing the same commands is tedious and, frankly, error-prone.
Oh yeah, definitely. That's the perfect use case for the interface range command. This is a massive time saver.
How does that work?
You can use syntax like interface range gigabyte Ethernet 105.15, and then every subsequent subcommand you enter while in that range, mode-like description interface not in use or shutdown, is applied instantaneously to all 11 of those ports simultaneously.
Ah, brilliant. One command hits multiple interfaces.
It's essential for any kind of batch configuration management. Saves time, reduces typos.
Okay, next up. Controlling the interface state itself. If I need to administratively take a port offline, maybe for maintenance, or perhaps to isolate a device that's causing problems, how do I actually disable it?
That is the shutdown command, entered in the interface configuration mode. It is the administrative off switch for the port.
And what happens to the status when I do that?
When applied, the interface is disabled and its status changes dramatically. In the detailed show interface's output, you'll see administratively down. In the summary show interface's status output, it's simply listed as disabled.
So that clearly indicates that you, the administrator, explicitly took the port offline, separating it from, say, a physical cable issue.
Correct. It's an intended state.
And that famous, slightly weird networking syntax to bring it back online?
Hey. Yeah, the slightly backward but totally universal no shutdown.
Not enable or turn on.
Nope. It seems odd at first, but
Yeah.
no is the standard prefix used across Cisco iOS and many other network operating systems to reverse a configuration command or revert something back to its default setting. So no shutdown reverses the shutdown command. You get used to it quickly.
Which brings us neatly to the final point on cleanup. If I manually set speed 100 and duplex full on a port, maybe for testing, how do I cleanly revert that port back to its original factory state, which is usually auto-negotiation?
Use that same no command logic. Entering no speed under the interface configuration will remove the manual speed setting and revert the port back to its default, which is speed auto.
And no duplex reverts to duplex auto.
Exactly. And if you remove the description, no description will remove that text. If you have multiple custom settings on an interface speed, duplex, maybe some security features, description, and you just want to wipe the slate clean back to factory defaults,
Is there a shortcut?
there is. You can use the command default interface 8. For example, default interface gigabit Ethernet 101. That single command wipes out all user-configured subcommands on that specific port and restores every setting to its original factory default state.
Ah, that's extremely handy for a quick, clean reset of a port.
Very useful, yeah.
Mm-hmm.
So we've talked a lot about speed and duplex negotiation, but we can't discuss the physical layer, layer 1, without addressing the cabling itself. For years, network engineers carried around, two distinct types of copper Ethernet cables, straight through and crossover.
Oh, yeah, I remember the color-coded bags. This was based entirely on the types of devices being connected, right?
Yeah, exactly. For connections between what we call disparate devices, like a switch connecting down to a PC or a server or a router connecting to a switch, you used a straight-through cable. The pinout was, well, straight through. Pin 1 to pin 1, pin 2 to pin 2, and so on. Transmit on one end connected to receive on the other implicitly.
Okay.
But for connecting similar devices, like linking two switches together or connecting a switch directly to a router's Ethernet port or even two PCs directly, you needed a crossover cable.
Because their transmit pins would otherwise connect to each other.
Precisely. The crossover cable internally swapped the transmit and receive pairs. So the transmit pins, usually 1 and 2 on one device, would land on the receive pins, usually 3 and 6 of the other device, and vice versa. Get this wrong. Use the wrong cable type for the connection.
And the link simply never came up. Lights stayed off. The legendary failure state. Dude, you got the wrong cable.
Exactly. Which leads us to Auto-MDIX, Automatic Medium Dependent Interface Crossover. This is honestly one of the greatest quality of life improvements in modern networking hardware.
So what does it do?
Auto-MDIX is a feature implemented right in the interface electronics, the PHY chip. It automatically senses the electrical pinout of the connected cable and the device on the other end. If it detects an incorrect cable type for the connection, say, you accidentally plugged a straight-through cable between two switches.
Which normally requires a crossover.
Right. The interface electronics automatically reconfigure the internal pin assignments, essentially performing the necessary crossover function electronically within the chip. It swaps the pairs internally.
Wow. So if I accidentally grab the wrong cable type from the box, the physical interface itself just figures it out and electronically fixes the pinout problem for me.
That's the beauty of it. It makes cabling almost foolproof for standard connections. And the good news is pretty much all modern Cisco Catalyst switches, and most other vendors' switches too, use MDIX Auto as the default setting on their copper ports.
Is it on by default?
Yes, MDIX Auto is the default. And here's the really key redundancy feature. Auto-MDIX works and corrects the cabling issue if either one or both endpoints have it enabled.
Oh, that's good. So even if I'm connecting my new switch to a really old switch that doesn't support Auto-MDIX.
As long as your new switch has Auto-MDIX enabled, which it does by default, it will detect the situation and fix the connection, regardless of the cable type you used. It only takes one side to solve the problem.
So in a modern network environment where Auto-MDIX is pretty much universally enabled by default, getting that not connect state purely because of a cable pinout error is actually quite difficult to achieve accidentally.
It is incredibly resilient these days. To actually observe a link failure caused specifically by the wrong cable pinout, you'd have to go out of your way to manually disable the feature using the no MDIX auto interface subcommand.
And you'd have to do that on both ends of the link.
Yes, exactly. Only if Auto-MDIX is disabled on both switches and you then plug in the wrong cable type, like a straight through between them, only then will the link fail to establish and present that classic not connect state due to the pinout mismatch.
Okay, now we move into the actual detective work, analyzing what the switch is telling us about the health of the connection. We need to use the detailed output commands like show interfaces. And we often see that two-part status code when we check a specific interface, right? Like up, up, or down, down.
That's the crucial two-code system you see in show interface at IEEE. It's always line status followed by protocol status.
Line status, protocol status, what do they mean?
The line status is purely layer 1. Is there a physical connection? Is the electrical signal detected? Is the light level on the fiber okay? Basically, it's the physical layer working.
Okay, layer 1 check.
The protocol status is layer 2. Assuming the physical link is up, are the necessary data link later protocols running correctly over that link? This could be basic line protocol keep alives, or even things like spanning tree protocol interactions, if it's a switch-to-switch link. Are layer 2 frames actually being exchanged successfully?
So the ultimate goal, the perfectly healthy state, is up-up.
Exactly. Up-up means the physical layer is solid, line status up, and the data link layer protocols are happy and exchanging frames correctly, protocol status up. This corresponds to that single word code connected that you see in the summary command, show interfaces status.
Right. And if we see administratively down, down.
We know immediately that was an intentional action by administrator. The shutdown command was run on that interface. The single code in the summary is disabled.
Okay. Now, the most common failure state we encounter is probably down, down, which correlates to that single code not connect in the summary view. What are the primary suspects when we see that down, down, or not connect?
You always start with the simplest layer 1 physical failures. The absolute most common are there's literally no cable plugged in or the cable is broken.
Check the physical connection first.
Always. Then check the other end. Is the neighboring device actually powered on? Is the interface on the other end maybe shut down administratively?
Good point. The problem might be on the neighbor.
Definitely. And if, for some reason, Auto-MDIX has been disabled on both ends, then down, down could absolutely be caused by using the wrong cable pin out, straight through versus crossover. Less obvious physical causes could include severe signal degradation due to excessive EMI, electromagnetic interference.
Like running the copper cable right next to a big motor or fluorescent light ballast.
Exactly. Strong electrical noise can corrupt the signal so badly layer 1 just fails. Or in the case of fiber optic cables, you might encounter macro bending.
Macro bending! What exactly is that again?
It's physically bending the fiber optic cable too tightly, usually exceeding its minimum bend radius specification, like pulling it taut around a sharp 90-degree corner in a rack or conduit.
And that causes problems how?
Light travels down the fiber core by reflecting internally off the boundary with the cladding layer. If you bend the cable too sharply, the angle of incidence becomes too shallow, and the light literally leaks out of the side of the fiber instead of reflecting. The receiver sees this as a significant loss of light signal, interprets it as a physical failure, and the interface goes down, down.
Okay, so down, down, or not connect is usually a pretty clear physical problem, or maybe a speed mismatch, preventing the link formation entirely. But we established earlier that the real insidious threat is the link that looks fine, it's up-up, but it's secretly diseased because of that duplex mismatch crisis. How does the network detective spot that hidden operational failure?
Right, since the link status codes look perfectly healthy, up, or connected, we can't rely on them at all for this particular problem. We have to dig deeper. We must become like forensic accountants and analyze the interface error counters in the detailed show interfaces output.
Which counter is the smoking gun for duplex mismatch?
If you suspect a duplex mismatch is causing terrible performance on an up link, the #1 screaming siren you must look for is a constantly increasing late collisions counter.
Late collisions. Let's delve back into the logic of that. Why are late collisions the specific fingerprint of a duplex mismatch, and not just regular collisions?
This goes back to the rules of CCNA, which remember is only supposed to be active in half-duplex links. The IEEE Ethernet standard dictates that in a properly functioning half-duplex Ethernet segment, any legitimate collision, where two stations transmit almost simultaneously, should be detected very, very early in the transmission process. Specifically, it must be detected within the first 64 bytes of the frame being sent. The 64-byte window is called the collision domain slot time.
Okay, so normal collisions happen fast, within the first 64 bytes.
Right. If a half-duplex device detects a collision after it has already successfully transmitted the first 64 bytes of its frame, it flags that event as a late collision.
And since a duplex mismatch involves one side being full duplex, which doesn't run CSMAN-Z and transmits whenever it wants, and the other side being half duplex, which is running CSMAN-D and expects collisions only in that first 64-byte window.
Exactly. The half-duplex device starts sending. The full duplex device might start sending at the same time or even slightly later, completely ignoring the half-duplex device's transmission. Because the full duplex device keeps transmitting well beyond that initial 64-byte window, the collision is detected by the half-duplex port late in its own frame transmission. A constantly increasing late collisions counter is virtually a 100% guarantee, maybe 99.9% guarantee, that you have a duplex mismatch. One end is set to full duplex and the other end is operating in half duplex. It's the most reliable indicator.
That is such a crucial distinction for troubleshooting. Fix the duplex settings, clear the counters, and watch if lead collisions stop incrementing.
Bingo!
Now, what about the other vital error counters that often show up in show interfaces? We sometimes see input errors, CRC errors, runts, and giants all grouped together. How do we differentiate those?
Yeah, it is vital to separate these in your mind when troubleshooting. If you see the main input errors counter growing, the first thing you should check is the specific CRC errors counter, which is usually listed nearby or as a component of input errors.
CRC cyclic redundancy check.
Right. Every Ethernet frame has a checksum called the frame check sequence, FCS, appended to the end. It's calculated based on the frame's data bits. CRC errors mean the receiving device read the frame, performed the same mathematical check, and the result didn't match the FCS value in the frame. This means the bits got corrupted somewhere during transit.
So what causes CRC corruption if it's not a duplex mismatch?
Generally, CRC errors that are increasing without a corresponding increase in late collisions usually point to a purely physical layer interference or quality problem. Could be a poorly crimped connector on the cable. Maybe one of the pairs isn't seated right. Could be high levels of EMI from electrical noise sources running too close to the cable path. Could be physical damage to the cable itself, a kink, a staple through it, or maybe just a bad port on the switch or NIC or a faulty patch panel connection.
So if you're seeing high CRC errors, but no late collisions, you should probably be thinking about replacing the cable first, or checking the physical path for noise sources.
Exactly. The problem is almost certainly related to physical damage, poor cable quality, or external electrical interference.
Okay, so just to summarize the digital detective work on these key counters, late collisions point strongly to a configuration problem, the duplex mismatch. CRC errors, without late collisions, point strongly to a cable quality or environmental noise problem, physical layer issue.
That's a perfect summary. We also sometimes see runts, which are received frames that are smaller than the minimum legal Ethernet frame size of 64 bytes. Runts are often indicators of collisions, especially normal collisions in a busy half-duplex environment where two stations might start transmitting too close together, detect a collision quickly, and abort, leaving a truncated frame fragment on the wire.
Okay. And finally, giants.
Giants are the opposite. Received frames that exceed the maximum standard Ethernet frame size, which is typically 1518 bytes, or slightly larger if VLAN tagging or jumbo frames are involved. Seeing giants often points to a misconfiguration of the maximum transmission unit, MTU, somewhere on the network path, or possibly faulty hardware on the sending device that's just generating illegally oversized frames.
Got it. So the ability to analyze these different counters, knowing which one is rising and what that specific symptom most likely implies, is really the difference between spending 5 minutes fixing a duplex setting versus spending 5 hours painstakingly tracing a cable path that turns out to be perfectly fine.
Absolutely. Understanding these counters is key to efficient troubleshooting. Tag outro.
Well, this deep dive has certainly stripped back the layers of basic network connectivity. We started with the real elegance of auto-negotiation, where devices use those fast link pulses to quickly agree on the best common speed and duplex.
You'll stay.
But we also exposed the systemic weakness in that fallback mechanism, parallel detection, particularly its default to half duplex at 10 and 100 megabits per second. A seemingly innocent rule that directly leads to that devastating hidden performance killer we call a duplex mismatch.
And the key to maintaining operational confidence, really, lies in verification and careful inspection. Remember that little A prefix in your show interface's status output? It's your fastest check on whether a signal was learned dynamically or manually applied by you or someone else. And when you're troubleshooting a link that seems connected but is just unbelievably sluggish, your most powerful diagnostic tool is almost always going to be that late collisions counter in show interfaces. An increase there is an immediate, pretty much unassailable sign that you've got a configuration problem, specifically that duplex mismatch, on your hands.
It really is all about mastering these low-level defaults and behaviors so that when the automation fails or when someone makes a manual configuration mistake, you know exactly where to look and, more importantly, why you're looking there.
And that leads us nicely into our final provocative thought for you, the listener, to consider. We briefly touched on the fact that hardware itself can sometimes behave differently based on its specific features. For instance, we know that some complex switch ports, like those providing power over Ethernet, PoE, might actually retain certain auto-negotiation capabilities even when you manually input static speed and duplex commands.
Oh, interesting. So you type speed 100, duplex full, but the PoE port might still be trying to do some auto-sensing behind the scenes.
Potentially, yes, depending on the specific hardware implementation. Meanwhile, the adjacent non-PoE ports on the very same switch might fully respect your static configuration and completely disable all auto-negotiation functions as expected. This means you can end up with variable, inconsistent behavior across different ports despite applying identical configuration commands.
Wow, that inconsistency sounds like an operational nightmare if you're trying to enforce a strict standard.
It absolutely can be. So the question for you is, how might a conscientious network engineer proactively design a standard operating procedure or perhaps a configuration template, something more robust than simple trial and error after deployment, that guarantees consistency and reliability across a diverse fleet of switches where these subtle hardware-specific behaviors might dictate whether a crucial configuration setting is actually honored or potentially ignored by the underlying silicon?
How do you standardize the human input and verification process when the hardware itself introduces this kind of variable complexity underneath?
That's the challenge. A question of standardization versus needing to adapt to hardware quirks. Something to definitely chew on as you go about checking your late collisions counters.
Indeed. Thanks for joining us on this deep dive.